Hello everyone, and welcome back to Module 2. Over our last few lectures, we've looked at the rigid geometry of the Perovskite crystal lattice and how we can chemically engineer its bandgap. But today, we are going to answer the biggest question in modern photovoltaics. Why do these materials work so incredibly well? Take a look at the chart on your screen. This represents the historical evolution of solar cell efficiencies. If you look at traditional materials like crystalline silicon or cadmium telluride, you see a slow, grueling, decades-long climb to reach 20% efficiency. Then, look at the orange line. That is the metal halide Perovskite curve. It is a near-vertical explosion. In 2009, the first Perovskite solar cell achieved a meager 3.8% efficiency. In just over a decade, it shattered the 26% barrier, rivaling the absolute best silicon devices ever manufactured. What makes this trajectory truly unprecedented is that early Perovskite films were not perfectly engineered single crystals. They were messy, defect-ridden, solution-processed films made in basic chemistry labs. The fact that they performed so brilliantly proves that their success is not just a result of clever device engineering. It is fundamentally rooted in the intrinsic, incredibly forgiving quantum physics of the Perovskite lattice itself. Today we are going to look under the hood. We are going to examine the 4 key physical properties that make perovskites the closest thing to a perfect semiconductor we have ever discovered. Let's begin at the very first step, the moment light is absorbed. When a photon is absorbed by a semiconductor, its energy excites an electron across the bandgap, leaving behind a positively charged vacancy known as a hole. However, the most critical question in device physics is, what happens next? Do that electron and hole remain bound together, or do they separate freely? Because the electron is negatively charged and the hole is positively charged, they naturally attract each other. In many materials, particularly in organic photovoltaics, or OPVs, this attraction is incredibly strong. The electron and hole become locked in what we call a Coulombic embrace, forming a tightly bound, neutral quasiparticle called an exciton. In organic solar cells, the binding energy holding this exciton together is massive, typically around 300 millielectron volts. As long as they are bound, they cannot generate electrical current. To rip them apart, device engineers are forced to create complex bulk heterojunction interfaces to physically strip the charges away from each other, which inherently costs voltage and efficiency. Now look at the right side of your screen, the Perovskite advantage. Perovskites behave entirely differently. In a standard metal halide perovskite, the exciton binding energy is exquisitely small, only about 10 to 20 millielectron volts. Why is that specific number so important? Because we must compare it to the ambient heat of the environment. At standard room temperature, the ambient thermal energy of the universe, calculated as Boltzmann's constant times temperature, provides a continuous kinetic background vibration of roughly 26 millielectron volts. Because the 26 millielectron volts of room temperature heat is greater than the 15 millielectron volt binding energy, the perovskite exciton is literally shattered by ambient heat within femtoseconds of its creation. The material spontaneously generates free, highly mobile charge carriers entirely on its own, without needing complex internal interfaces. But why is this binding energy so magically low? The answer lies in dielectric physics. To understand why perovskites generate free charges so easily, we look at the Wannier-Mott equation. This equation models the strength of the exciton binding energy, denoted as E sub B. It states that the binding energy is proportional to the reduced effective mass of the carriers, divided by the square of the material's relative dielectric constant, which is represented by the Greek letter epsilon sub r. I want you to focus entirely on that denominator, the dielectric constant. In physics, the dielectric constant measures a material's ability to polarize, to shift its internal electric fields in response to an external charge. Organic polymers are highly rigid in their charge distribution. They have very low dielectric constants, usually around 3. This means they offer weak screening, allowing the electron and hole to feel the full, crushing force of each other's electrostatic pull. Perovskites, on the other hand, are heavy, soft, ionic crystals. Their lattice is incredibly polarizable. The massive lead and iodine ions can physically shift, and their large electron clouds can easily deform. This grants perovskites an exceptionally high dielectric constant, often approaching 30. Now apply this to the math. Because the dielectric constant is squared in the denominator, a 10-fold increase in the dielectric constant, going from 3 to 30, produces roughly a 100-fold reduction in the binding force. The heavy, flexible perovskite lattice essentially acts as an electrostatic shield, perfectly insulating the electron and hole from one another. This is the physical mechanism that allows them to separate easily and behave as totally free particles. So ambient heat has successfully separated our charges. The next question is, how efficiently do they move through the crystal to reach the external circuit? Carrier transport is dictated by the shape of the material's electronic band structure. If you look at the energy momentum, or EK diagram on the screen, you will notice the steep, parabolic curvature of both the conduction band at the top and the valence band at the bottom. In solid-state physics, the curvature of these bands directly dictates a property called the effective mass of the charge carrier. A flat, shallow band produces a heavy carrier that moves sluggishly. A steeply curved band produces a carrier that accelerates incredibly fast. In perovskites, because of the massive, highly expansive orbital overlap between the lead and the iodine atoms, these bands are incredibly steep. As a result, the effective mass of the carriers is extremely small, roughly 0.15 times the rest mass of a free electron. Because they are so light, these carriers accelerate effortlessly under the built-in electric field of the solar cell. But what makes perovskites truly special is something called ambipolar transport. In many traditional semiconductors, there is an imbalance. Electrons might be fast, but holes are sluggish, creating a microscopic traffic jam that limits the overall current. In perovskites, both the conduction band and the valence band share that same steep curvature. Therefore, both the negative electrons and the positive holes sprint through the material with nearly identical, exceptionally high velocities. This perfectly balanced transport dramatically reduces the chance of charges crashing into each other and recombining. This brings us to the ultimate metric of any photovoltaic material, the carrier diffusion length, denoted by the capital letter L. The diffusion length tells us the exact physical distance a charge carrier can travel through the crystal before it inevitably hits a defect, loses its energy, and recombines. It is calculated as the square root of the diffusion coefficient, d, multiplied by the minority carrier lifetime, tau. Perovskites excel at both of these variables. First, as we just learned, their incredibly low effective mass gives them a massive diffusion coefficient. They move fast. Second, perovskites possess a unique property called defect tolerance. When defects do form in the lattice, they tend to form shallow energy traps rather than deep ones. This means charges rarely get permanently stuck, leading to incredibly long carrier lifetimes. When you multiply a high velocity by a long lifetime, you get an extreme diffusion length. In high-quality perovskites, diffusion lengths easily exceed 1 full micrometer. Why is this the ultimate triumph for this material? Look at the graphic at the bottom of the slide. Because perovskites are incredibly strong light absorbers, a solar cell only needs to be roughly 0.3 micrometers thick to absorb 99% of the incoming sunlight. If your film is only 0.3 micrometers thick, but your charges are capable of traveling for over 1.0 micrometers, they can travel 3 times further than the actual thickness of the cell. This virtually guarantees that almost every single electron and hole generated by the sun will successfully reach the extracting electrodes. Consequently, the internal quantum efficiency of the device approaches absolute perfection. Let us summarize the physical picture we have built today. We can now fully understand why perovskites are often referred to as a miracle semiconductor. They combine a rare suite of advantages. First, massive dielectric screening crushes the excitant binding energy, enabling the spontaneous generation of free charges at room temperature. Second, optimal orbital overlaps create incredibly light effective masses, resulting in high-speed ambipolar mobility. Third, defect tolerance extends the carrier lifetime, yielding extreme diffusion lengths. Together, these forgiving optoelectronic properties perfectly explain the vertical rise in solar cell efficiency we observed on our very first slide. However, no material in the history of science is completely perfect. If their optoelectronic physics are this flawless, why aren't perovskite solar panels powering your home right now? Because the very same soft, flexible lattice that grants them these incredible properties also makes them exquisitely vulnerable to the environment. In our next and final lecture of Module 2, we will examine the dark side of this material. We will explore the major challenges that currently limit their commercialization, focusing on structural phase transitions, moisture degradation, and the infamous Achilles' heel of perovskite stability. Thank you for your time, and I will see you in Lecture 2.5.